Hello, hello, my dear friends. Before going to the example mentioned here, I would like to define two more terms in case of group theory. Two terms. One, order of order of a group. And order of an element in a G. Order of an element in a group G. G. One definition. One, in a group G, with star as a binary operation, if G is a finite set, then we say that G is a finite group. Finite group. And if cardinality of G is M, let us say, then order of group G is defined to be like this. M is some fixed integer. Okay, M is some fixed integer. And second definition, in a group G, group in a finite group J, we can say, in a finite group J, J, if an element A belonging to J, then order of A is denoted by order of A and defined to be what's that defined to be? The least positive integer. Least positive integer k such that a raised to k equal to e. Note that k is the least positive integer. Then we say that, then we write order of a equal to k. For example, we have a group J, cleans four group E, A, B, C, okay, in which order of A is 2, order of B is also 2, and order of C is 2, okay. And it is going to be more clear if we consider another example, G equal to 1, minus 1 I and minus I. It is a group with respect to multiplication, as you have already seen. Now order of an identity 1, always 1. Order of identity is always 1. Now ಅಂದ್ರೆ ಇಲ್ಲಿ ನೋಡಿ order of 1 is 1. Order of minus 1 is 2. ಯಾಕಂದ್ರ ಇಲ್ಲಿ ನೋಡಿ ಇಲ್ಲಿ minus 1 raised to 2 is equal to 1 identity. Okay. Now observe one more thing. Minus 1 raised to 4 equal to minus 1 raised to 2 into minus 1 raised to 2. Minus 1 raised to 2 is a 1, and this is also 1, and this is 1. Now observe, minus 1 raised to 2 is 1, and minus 1 raised to 4 is also 1. Here we can't say order of minus 1 is 4 because 2 is the least integer for which power is 1. And similarly we can see here, order of I is 4. Why order of I is 4? Now here I square is equal to minus 1 by the definition. I is a complex imaginary number, and I raised to 4 I can write down. This is I raised to 2 into I raised to 2. Okay, that equal to minus 1 into minus 1, that is 1, and therefore order of I is 4. Okay, and also I raised to 8 is also 1, but 4 is the least integer, and 8 cannot be order, and 4 is the order of that. Similarly, order of minus I is also 4. One more thing, note here. Note here, note that in G, order of any element A equal to order of A inverse, which you can prove later on this. And also we will discuss about the order of an element in detail while we are dealing with subgroups. Okay, now it is sufficient to know the order of an element in a group which I have mentioned earlier. Okay. Now we will go to next example. As I have already told, here G contains plus or minus 1, plus or minus I, and plus or minus J, plus or minus K. Order of this group equal to 8 because 8 elements are there, and the relation defined by multiplication defined by minus 1 raised to 2 is a 1, I raised to 2 equal to j raised to 2 equal to k raised to 2 equal to minus 1, and ij equal to k. Cyclically you can say here I j k, ij equal to k, jk equal to I, and ki equal to j. Okay, like this we can multiply the elements here. Okay, and reversely, if you go on reversely, ik equal to my uh, ik equal to minus j, and ji equal to minus k, kj equal to minus I, and ki equal to minus j. With these relation, we can form a Cayley table here. Now, observe first row all the elements of G, and second row minus 1 into 1 minus 1 minus 1 into I minus I, and so on so forth. With this definition, we can form this Cayley table. Okay. Looking at this Cayley table, it is a group. Here, observe associative property holds good here, and identity is a 1. Identity is 1. 1 is the identity. It is very clear from the first row. 1 into any element will give the same element. First row uh, clearly says that 1 is the identity. First row in the Cayley table. Okay. And minus 1 raised to 1 equal to minus 1. I raised to minus 1 is equal to minus I raised to j equal to minus 1 equal to minus j, and k raised to minus k is minus k, and also reversely we can say. And furthermore, G is a non-abelian group. Yaka, why it is a non-abelian group? Illodile Ij equal to k I into j, k na, ji equal to j into k is equal to minus k, ji equal to minus k. Okay, therefore ij is not equal to ji, and therefore it is a non-abelian group. Therefore it is a non-abelian group. And some more non-abelian group we can deal later on. I mean, here what we have done, we have given the example of infinite group, namely Z plus, Q plus, R plus, C plus. C is a set of complex number. They're all infinite group because Z, Q, R, C are all infinite set. Okay. And finite group example, quaternion group and Kleen's 4 group. This is the quaternion group. Presently, now I am presenting here is called quaternion group. Okay, quaternion group, which is non-abelian, which you have shown here. Okay, and now we have dealt with a group of order 4 and group of order 8. What about group of order 5 and group of order 6? Of course, we'll give first example group of order 6, then we will go to group of order 5. Why we need some definition for that, and therefore we will consider later on. Okay. The symmetric group Sn. ಏನಿದು Sn symmetric group ಅಂದ್ರೆ S is a finite set consisting of 1 to n element. Integer, not necessarily integer, some symbols, a1, a2, etc., an you can take. Sn is set of all f functions. F from S to S is a permutation on S. What is a permutation? F from S to S is said to be permutation if f is both 1 1 and onto. If it is both 1 1 and onto, then we say that F is a permutation, where F is a 1 1 onto mapping. Then one can very easily verify that Sn is a group. What is the binary operation here? Binary operation is a composition of mapping. Composition of mapping is the binary operation in Sn. Okay. And one can verify that Sn is a group under composition of mapping. That is, if F and G belonging to Sn, uh, F composition G of X equal to F of G of X, product of mapping, in PUC level you have studied. Okay. This is the binary operation in Sn. Sn is a group. Why? Because composition of mapping is associative, whether 1 1 or onto. Naturally, 1 1 and onto functions are composition is associative function. That is, F composition G composition H equal to F composition G composition H. We can say product only. Instead of saying composition, we can say product. Product of mappings are associative property. This you can verify by taking some particular example. Okay. And next associative property is there, Sn one associative property. Associative property. And hence it is a semi-group associative property. Second, identity. What is the identity mapping? Identity mapping I is a mapping from S to S defined by I of X equal to X for every X. ಅದೇ ಎಲಿಮೆಂಟು ಅಂದ್ರೆ this is one way you can say constant or not constant, X onto X, Y onto Y. If there is a Z, Z onto Z. This is identity is identity permutation, you can say. In other words, you can say I equal to 1, 2, 3, etc. n, and 1 is a mapped onto 1, 2 is a mapped onto 2, 3 is a mapped onto 3, n is a mapped. This is known as identity permutation. That is identity element. We know that for every 1, 1, for every permutation, F 1 1 and onto, there is F inverse function F, which is also 1 1 and onto, and such that F composition F inverse is equal to identity mapping, and therefore Sn satisfying all the three conditions of the group functions, and therefore Sn is group. Sn is, we can say, a permutation group on n element. Now, particular example, let me take here. Note that it is a non-abelian group. This non-abelian group, we can prove that it is a very easy. Now, we can say I, J, K belonging to S consisting of 1, 2, 3, etc. n. Okay. Somewhere else, I, J, K are somewhere else. Now, alpha equal to ij means this is 1, 2, etc. I, etc. We can say I plus 1, etc. j, etc. n. I can write down. This 1 onto 1, 2 onto 2, etc. up to I minus 1, the same one. Here it is j. Other things are I. This is n. All are this. Alpha ij means this is I is mapped onto j, j is mapped onto I, all other elements are fixed, okay, here. And beta jk is similarly, we can, all other elements are fixed, j is mapped onto k is mapped onto j. Now here alpha beta of I equal to, by the definition of the composition of mapping, alpha of beta of I. Okay, beta of Y is a fixed here. Okay, that is alpha I. Alpha I equal to j. Okay, and beta into alpha of beta into alpha I, okay, equal to beta into alpha I. Okay, alpha I here, alpha I is j, alpha j. Alpha j is equal to here I, and therefore alpha beta I is not equal to beta alpha I, and therefore alpha beta is not equal to beta alpha, and therefore Sn is non-abelian group for n greater than or equal to 3. For n, it is going to be more clear if I take some particular example here. S3. S3 contains 1, 2, 3. Define a permutation. I, identity permutation. Each element is mapped onto the same element. F, here 1 is mapped onto 1 and 2 is mapped onto 3, 3 is mapped onto 2. And G, 2 is fixed, 1 is mapped onto 3, 3 is mapped onto this. H, here 3 is fixed, 1 is mapped onto 2, 2 is mapped. And phi, okay, phi here 1 is mapped onto 2, 2 is mapped onto 3, 3 is mapped onto 1. And psi, 1 is mapped onto 3, 2 is mapped onto 1, and 3 is. There are 6 elements, okay, there are 6 elements. In general, order of Sn, we will deal with that afterwards. N factorial elements. Here S3 is containing 3 elements, 3 factorial. Order of S3 equal to 3 factorial equal to 6 elements. All the 6 elements I have written here. All the 6 elements I have written. Now composition. Here we can say F square is equal to I. F I would like to take. F square equal to F into F. F is 1 is mapped onto 1, 2 is mapped onto 3, 3 is mapped onto 2. Again multiplication, 1 is mapped onto 1, 2 is mapped onto 3, 3 is mapped onto 2. What is the permutation which we are going to get? Multiplication of 2 permutation. First ಏನು ಮಾಡಬೇಕು, 1, 2, 3 ಬರ್ಕೊಂಡ್ಬಿಡ್ಬೇಕು. ಇಲ್ಲಿ ನೋಡಿ, ಇಲ್ಲಿಂದ ಸ್ಟಾರ್ಟ್ ಮಾಡಬೇಕು. 1 onto 1, 1 onto 1. Okay, 2 onto 3, 3 onto 2. Okay, 3 onto 2, 2 onto 3. ಇದು ಏನಾಯ್ತು ನೋಡಿ, I ಆಯ್ತಿಲ್ಲ, ಹೌದಾ? And therefore f square is equal to I identity. Okay, identity permutation. And fg ನೋಡೋಣ. fg equal to 1 2 3 1 f 3 2 by the definition of f. Okay, and g is 1 3 2 2 3 1. Okay, by the definition of g. Okay, equal to ಏನಾಗುತ್ತೆ, ನಾ ಏನು ಹೇಳಿದೆ ಆಗಲೇ, ಈಗ ಮೊದಲ 1 2 3 ಬರ್ಕೊಂಡ್ಬಿಡ್ಬೇಕು, ಇಲ್ಲಿಂದ ಸ್ಟಾರ್ಟ್ ಮಾಡಬೇಕು. 1 onto 3, 1 onto 3, 3 onto 2. Okay, and 2 onto 2, 2 onto 3. Okay, 3 onto 1, 1 onto 1. ಇದು ಯಾವುದು ನೋಡಿ ಇಲ್ಲಿ, 1 onto 2, 2 onto 3, 3 onto 1. ಯಾವುದಾಗುತ್ತೆ ನೋಡಿ ಇಲ್ಲಿ, 5 ಆಗುತ್ತಿಲ್ಲ ನೋಡಿ, 5 2 3 1 2 3 1. ಹೌದಾ? Multiplication of permutation can be done in this way, from right to left. From right to left we have to go. Okay. Similarly, what is that? fh equal to, ಇನ್ನೊಮ್ಮೆ ತಿಳಿಸ್ತೀನಿ, 1 2 3 1 3 2 f. h ಏನದ ನೋಡಿ ಇಲ್ಲಿ, h 1 2 3 2 1 3. ಓಕೆ, ಈಗ ನೋಡಿ ನಾ ಏನು ಹೇಳಿದೆ, ಬಲದಿಂದ ಎಡಕ್ಕೆ ಹೋಗ್ಬೇಕು. 1 2 3, 1 onto 2, 2 onto 3, 2 onto 1, 1 onto 1. Okay, and 3 onto 3, 3 onto 2. ಏನಾಯ್ತು, ದಿಸ್ ಈಸ್ ಅ ಸೈಜ್. ಓಕೆ, ಅರ್ಥ ಆಯ್ತಲ್ಲ ಹೆಂಗೆ ಮಲ್ಟಿಪ್ಲಿಕೇಶನ್ ಮಾಡ್ಬೇಕು ಅನ್ನೋದು. ಓಕೆ, ಆಲ್ ರೈಟ್. ವಿತ್ ದಿಸ್ composition of mapping, we can fi equal to g, psi equal to h. Similarly, we can write down all the possible product of this one. With these possible product, what I am going to write down, a composition table from the previous one. All these we can write down composition table. First row indicates that I is the identity. Second row, you can see f into I, f into f equal to I, means f square equal to I, which we have defined. fg equal to 5, fh equal to psi, f5 equal to g, and all those things which you can verify by direct multiplication of the permutations which I have already explained. Okay, now this is a group. Inverse of f is f, inverse of g is g, inverse of h is h, inverse of phi is psi, inverse of phi is psi, inverse of psi is phi. I is the identity. S3 is a non-abelian group. ಯಾಕಂದ್ರೆ ನೋಡಿ fg is equal to what is that? fg is equal to 5. Okay, and gf equal to psi. ಯಾಕೆ ನೋಡಿಲ್ಲ, fg is equal to 5, gf equal to psi, and fg is not equal to gf, and therefore this is a non-abelian group. We can say this is the smallest non-abelian group. If you take a group of order 5, that is always abelian, because all the groups of order less than or equal to 5, They are all abelian. This is the first example of non-abelian group. Maybe equal to, isomorphic to some other group of order 6 also. We will deal with later on here, which is isomorphic to this equivalent group, we can say. Okay, this is a non-abelian group of order 6. Okay, now very interesting example of a group I would like to give here. For that, I would like to define some binary operation here. Some binary operation, namely addition modulo n. Addition modulo n. Okay. What is addition modulo n? Observe Zn 0, 1, 2, 3, etc. n minus 1. How many elements? N elements. Addition modulo n is defined on this set, or I can say Zn cross Zn to Zn, defined by for every m and n, r and s I can take, r and s belonging to Zn, or rs, pair rs belonging to Zn cross Zn. Okay. Now, addition modulo n is defined to be rs is equal to least integer or least remainder when r plus s divided by n. It is k, let us say, the least integer. This is the addition modulo n operation in Zn. For example, we can take Z 6, okay, 0, 1, 2, 3, 4, 5, n minus 1. Okay, this addition modulo 6, or we can say this way, we can write down. Or some books they have written this like this, addition suffix 6. Okay, now 3 and 5 belonging to Z6, 3 plus 6 is equal to 5 is equal to 3 plus 5 equal to 8 divided by 6 least integer, least remainder. ಏನಾಗುತ್ತೆ ನೋಡಿ, 6ಕ್ಕೆ 8ಕ್ಕೆ 6ರಲ್ಲೇ ಭಾಗಿಸಿದ್ರೆ ರಿಮೈಂಡರ್ ಎಷ್ಟು ಉಳಿತದ? 2 ಅಲ್ಲ, ರಿಮೈಂಡರ್ ಇಸ್ 2, ಹೌದಿಲ್ಲ? ಆಮೇಲೆ 4 and 5, okay, 4 plus 5 equal to 4 plus 5 ಅಂದ್ರೆ divided by 9, or 4 plus 5 is 9 divided by 6. ಇಲ್ಲೇ ಡಿವೈಡ್ ಮಾಡಿದ್ರೆ ರಿಮೈಂಡರ್ ಎಷ್ಟು ಉಳಿತದ? 3 ಉಳಿತದ, ಹೌದಲ್ಲ? ಇದೇ ಥರ ಈ ದಿಸ್ ಈಸ್ ಎ ಬೈನರಿ ಆಪರೇಷನ್ ಇನ್ Zn. ಓಕೆ, now you can see here 2 plus 3 is equal to 1, ಯಾಕಂದ್ರೆ 3 plus 3 is equal to this example 2, etc. And moreover, ಇಲ್ಲಿ ನೋಡಿ, ಈ ಏನು ತಗೊಂಡಿದ್ದೀನಿ, Z4 ತಗೊಂಡಿದ್ದೀನಿ. ಇಲ್ಲಿ ಏನಾಗುತ್ತೆ 0 1 2 3 ಅಂದರೆ ಅಡಿಷನ್ ಮಾಡ್ಯುಲೋ 4. ಓಕೆ, ಇಲ್ಲಿ 0 plus 0 is equal to 0. For each k greater than 0, n minus k is the inverse of k. ಯಾಕೆ ನೋಡಿ ಇಲ್ಲಿ k plus n minus k equal to k plus n minus k equal to n divided by n equal to 0 ನ, ಯಾಕಂದ್ರೆ ರಿಮೈಂಡರ್ 0 ಆಗತ್ತಾ. ಆದ್ದರಿಂದ 0 is the identity. First row in this multiplication addition table, Kelly table, first row will clearly says that 0 is the identity here. Okay. In secondly, inverse of 1 is n is 4 in n is inverse of 1. n is 4, 4 minus 1 ಅಂದ್ರೆ 3. ಅಂದ್ರೆ 1 plus 3 is equal to 0. ಯಾಕಂದ್ರೆ ನೋಡಿ 1 plus 3 ಅಂದ್ರೆ 4 ಆಗುತ್ತೆ. 4 divided by 4, ರಿಮೈಂಡರ್ is 0. ಈಗ ನೋಡಿ 1 plus 3, 0 is there. Inverse of 2 is a 2 itself. Inverse of 3 is a 1. Now observe, order of 0 is 1 because identity element. Order of 1 is what? Order of 1 is order of 1. 1 plus 1 plus 1 plus 3. Okay. Order of 1 is because 4. Order of 1 is 4. 1 plus 1 plus 1 plus 1 is equal to 4. 4 divided by 4, remainder is 0. Similarly, we can find the order of 2. Order of 2 is 2 only, and order of 3 is 1. Like that, you can see for each element, you can find out the order. In general, okay, in general, Zn addition modulo n is a group. How many elements are there? Order of Zn is n element. This is a finite group of order n. ನಾನು ಈಗ ಹೇಳಿದೆ group of order 5. Group of order 5 is this. You can take Z5, which will form a group under addition modulo 5. That is 0, 1, 2, 3, 4. This is a group of order 5 with respect to addition modulo 5. Okay, addition modulo 5. This is a very important group. We will see furthermore, it is a abelian group. ಯಾಕೆ abelian group? ಇಲ್ಲಿ ನೋಡಿಲ್ಲ, a plus b is the least positive integer or least remainder when divided by n. Okay, ಅಂದ್ರೇನು a plus b equal to n equal to r. Okay, that is a plus b. Okay, and b plus a ಏನಾಗುತ್ತೆ ನೋಡಿ, this is b plus a divided by n is also r. A plus b divided by n, the remainder is same. B plus a divided by n, remainder is same, and therefore A plus B is equal to B plus A, and hence it is abelian group. Zn is for any integer n. Zn is abelian group. Okay, ಅರ್ಥ ಆಯ್ತಲ್ಲ. ಇದು addition modulo n. Addition modulo n ಅಂದ್ರೆ binary operation is addition of any two elements in the set Zn divided by n. The value is the least remainder. So value is always belonging to Zn, and hence it is a binary operation. Associative property one can verify, and also identity is a 0, and inverse of each element which you can get it. Inverse of k is n minus k for every k. Okay, inverse exists, identity exists, associative law exists, and therefore it is a group. Furthermore, not only group, it is a abelian group which you can see here. Okay, now you can see one more binary operation, multiplication modulo n. Multiplication modulo n, the same way we can see A and B belonging to Zn. Zn is 0, 1, 2, etc. n minus 1. Multiplication modulo n is multiplication of integer divided by n equal to r is the least remainder. For example, Z4 0, 1, 2, 3. ಈಗ ನೋಡಿ 2 into not plus equal to 2 into 3 divided by 4 equal to 6 divided by 4. Value is a 2. 1 into 2 this one, and 2 into 3 here, and 3 into 3 9. 9 divided by 4 means remainder is 1 only. Remainder is 1. Now, is it a group? Of course, we have got a binary operation, and we have, what is that? Associative property is also there, because integers, product of integer is associative property. Next question is, has it have a identity element? Not a group. 0 has a no inverse. 0 has a no inverse, because A belonging to Z4, 0 into this is 0 into, not addition, into A equal to 1. 1 is the identity element here. 1 is the identity element. Inverse property fails here, and hence it is not a group. Okay. Now, though it is not a group, let me consider Z5. Okay, Z5 equal to 1, 2, Z5 equal to, Z5 equal to, I would like to write down here, it is something wrong. Notation is Z5 minus 0. Let me consider. Z5 minus 0 means Z5 has 0, 1, 2, 3, 4. Okay. Z5 minus 0 means 1, 2, 3, 4. Is it a group with respect to multiplication modulo 5? Now you can see here Z5 is this set. Okay. Now I would like to write down multiplication table here. 1, 2, 3, 4. 1, 2, 3, 4. Multiplication modulo this. 1 into 1, 1. 1 into 2, 2. 1 into 3, 3. 1 into 4, 4. 2 into 1, 2. 2 into 2, 4. 2 into 3, 6 divided by 5. 1. Remainder is 1. Okay. Not 6 by 5 is equal to 1 alla. Remainder are equal to 1. Okay. This 1. And 2 into 4, 8. 8 divided by 5 is a 3. Okay. 8 by 3 divided by 5. Remainder is 3. Means 2 into 4 is equal to 8 divided by 5 equal to R is equal to 3. 3 into 1, 3. 3 into 2, 6. 1. 3 into 6, 1. And 3 into 3, 9. Remainder is 9 divided by 5. 9 divided by 5. Remainder is 4. 3 into 4, 12. Remainder is 2. Okay. And 4 into 4, 4 into 2, 4 into 2, 8, 8 divided by 5, remainder is 3. 4 into 3, 12, 12 divided by 5 means 2, this is 1. 4 into 4 is 16, 16 divided by 5, remainder is 1. Now you can see here, this is a group. Whereas Z5 with respect to multiplication is not a group. But Z5 ದೊಳಗ 0 ತೆಗೆದು ಮಲ್ಟಿಪ್ಲಿಕೇಶನ್ ಮಾಡ್ಯುಲೋ 5 ತಗೊಂಡ್ರೆ ಗ್ರೂಪ್ ಆಗುತ್ತೆ ಇಲ್ಲ ನೋಡಿ. 1 is the identity, 1 is the associative property naturally holds. Inverse of 2 is 3, 2 inverse is 3, 3 inverse is 2, 4 inverse is 4. ಹೌದಾ? All the elements have inverse element. 1 is the identity element and hence it is a group. Z5 minus 0 is a group with respect to multiplication, but not Z5. Z5 with respect to multiplication is not a group because inverse element does not exist here. Now I will stop here by giving one example here. Question, I would like to put question here. Is Z6 minus 0 a group with respect to multiplication modulo 6? If it is not, why? Question. Whether it is Z5 minus 0 is a group with respect to multiplication modulo 6 we have already proved. 5 we have already proved. But Z6 minus 0, is it a group with respect to the same binary operation modulo multiplication modulo 6? Question. I will leave it as. And also verify about Z7 minus 0. Is it a group? Is it a group? QN, another one question. Question 2. Is it a group? With respect to multiplication, these two questions, I will leave it for your exercise. If you say yes or no, let me know tomorrow. Okay? One more example I would like to give you here, and let me stop at that stage. Example of a group. Okay? Let M be set of all A such that matrix A is a matrix of order M cross N, where all ijth element I and j belonging to set of real number, or I can say A equal to set of all Aij Aij are all real number. This is also denoted by M cross N, means M rows and N columns. M rows and N columns. Addition of matrices, means entry wise addition. For example, you can say 1, 2, 4, 5. It means 2 cross 2, M equal to 2, N cross equal to 2. And 0, 1, 5, 2. This addition is 1 plus 0, 1, 2 plus 1, 3, 4 plus 5, 9, 5 plus 2, 7. Entry-wise addition. You are familiar with this operation. Okay? This operation. Okay. M cross N. Binary operation here on M is given by addition of matrices. Addition of matrices, you know it very well. Element wise addition. Element wise addition. Now, here M plus is a group. How you can say a particular example? Let me take M equal to 2 cross 3 matrices. Entries of A are real numbers. Addition of this, okay? A equal to, let me say A equal to A1, A2, A3, B1, B2, B3. Means two rows and three columns. Okay. B equal to C1, C2, C3, D1, D2, D3. Okay. Now A plus B is defined by A plus A1 plus C1, A2 plus C2, A3 plus C3, and B1 plus D1, B2 plus D2, C2 plus D. I'm sorry, B3 plus C3, D3. So again it is uh, 2 cross 3 matrices, and therefore A plus B belonging to M, and therefore it is a binary addition of matrices, any form of matrices, square matrices or any other from M cross N matrices. The addition is this one. Verify that. Is it a group? Yes. Then M plus is a group. What is the identity element? What is the inverse? Verify this. I will leave it as an example. Okay. Let me stop today, and we'll discuss some more examples of very interesting examples of groups on matrices only, and some more examples we'll deal with tomorrow. Thank you for patient hearing. Okay, let me stop here.